In 1935, Albert Einstein made a mistake. Well, not exactly a mistake. More like he built something he never intended to build. He was sitting at the Institute for Advanced Study in Princeton, New Jersey, 2 years into his self-imposed exile from Hitler's Germany, working with a young physicist named Nathan Rosen. And together, they were trying to solve one of the most annoying problems in all of physics: singularities, points in the math where numbers blow up to infinity, points that shouldn't exist if the universe makes any sense at all. Einstein hated them. He thought they were ugly, unphysical, a sign that the equations were broken, that something had gone wrong in the theory of general relativity he had published 20 years earlier. So he and Rosen performed a clever mathematical trick. They took the equations describing the space around a massive object, applied a coordinate transformation that replaced the radial variable r with a new variable u squared equals r minus 2m, and removed the singularity entirely. And in doing so, they accidentally created the blueprint for a shortcut through the universe. Their paper, published on July 1st of that year in the journal Physical Review, described something nobody had imagined before: physical space as two flat sheets connected by a bridge. Not a bridge you could walk across, not a tunnel you could fly a spaceship through. Just a mathematical structure, a geometric curiosity buried in the equations of gravity. Einstein and Rosen called it a bridge. They used it to model elementary particles, not to plan interstellar road trips. They never once suggested anyone could travel through it. But the structure was there, sitting in the math, waiting for someone to ask the obvious question. What if you could? That question would consume theoretical physics for the next 90 years. It would inspire one of the greatest science fiction novels ever written, trigger a phone call that launched an entirely new branch of research, lead to a Nobel Prize winner spending 2 weeks arguing with Christopher Nolan about the speed of light, and eventually connect to the deepest unsolved mystery in all of physics: the question of what space and time actually are. Here is the strange truth. Wormholes are real. The same equations that predicted gravitational waves, which we detected in 2015, and black holes, which we photographed in 2019, also predict tunnels connecting distant regions of the universe. The math doesn't distinguish between these predictions. If you trust general relativity enough to believe in black holes, you have to take wormholes seriously too. But traveling through one would almost certainly kill you, and not in some dramatic, cinematic way. The universe has stacked so many obstacles between you and the other side of a wormhole that it almost looks intentional. Like the laws of physics are specifically designed to say, yes, we'll let this structure exist, but absolutely not. You cannot use it. And figuring out exactly why the universe draws that line is one of the most fascinating detective stories in modern science. To understand how we got here, we need to go back further than Einstein, because the first hint that something strange lurked inside the equations of gravity appeared almost 20 years before Einstein and Rosen published their paper, and nobody noticed. In 1916, just months after Einstein published his general theory of relativity and changed our understanding of gravity forever, an Austrian physicist named Ludwig Flamm at the University of Vienna was playing with the Schwarzschild solution. Carl Schwarzschild, a German astronomer and physicist, had found the first exact solution to Einstein's field equations while serving on the Russian front during World War I. He worked out the mathematics in the trenches, mailed the solution to Einstein, and died a few months later from a disease contracted in the field. His solution described the geometry of space around a perfectly spherical mass, and it would eventually form the mathematical foundation for understanding black holes. Flamm took that solution and constructed what we now call Flamm's paraboloid, an embedding diagram that showed the curved geometry of space near a massive object as a funnel shape. If you took two of these funnels and connected them at their narrowest points, you got something that looked suspiciously like a tunnel. Nobody paid much attention. Einstein himself likely never saw Flamm's work in this context. The idea sat dormant for nearly 2 decades until Einstein and Rosen stumbled onto it independently through their particle problem. But here is what makes the Einstein-Rosen bridge so conceptually wild. It emerges directly from the most fundamental equation in all of gravitational physics. Einstein's field equations relate the curvature of spacetime on one side to the distribution of matter and energy on the other. The equation looks elegant when you write it down. G mu nu equals 8 pi g over c to the 4th times T mu nu. The left side describes how space curves. The right side describes what matter and energy are doing. And because these equations are time-symmetric, meaning they work the same whether you run the clock forward or backward, they permit solutions that connect different regions of space and time through a narrow throat. This is not speculation. This is not a maybe. The wormhole solution satisfies Einstein's equations as rigorously as the solution describing Earth's orbit around the Sun. The math does not care whether we find the result convenient or intuitive. It simply produces structures, and wormholes are one of them. But the Einstein-Rosen bridge had a fatal problem, and it took almost 3 decades for anyone to prove it. In 1960, a mathematician named Martin Kruskal and independently a physicist named George Shekaris developed a new coordinate system for the Schwarzschild solution. The Kruskal-Shekaris coordinates, as they came to be known, revealed the complete structure of spacetime around a black hole for the first time. And that structure was far stranger than anyone had expected. It contained 4 distinct regions: our universe on one side, a second universe on the other, a black hole interior with a future singularity, and a white hole interior with a past singularity. The Einstein-Rosen bridge connected the 2 universes through the throat between the black hole and white hole regions. Think about what that means for a moment. A complete mathematical solution to Einstein's equations, worked out rigorously using the best tools in differential geometry, says that a black hole is not just a pit in space. It is a tunnel. On the other side of every black hole, there is mathematically another universe, a mirror reality accessible, at least on paper, through the interior of the black hole. The equations don't say maybe. They don't say under certain conditions. They say this is the full geometric structure of space and time around a spherical mass. 2 universes, connected by a bridge, with singularities waiting on either side. And here is the problem. 2 years later, in 1962, Robert Fuller and John Wheeler published a devastating proof in Physical Review. They showed mathematically that the Einstein-Rosen bridge opens and closes so quickly that not even light can make it through. At one moment in Kruskal time, two singularities join and a bridge forms. The throat reaches its maximum width, then it pinches shut again. The entire process happens faster than any signal could traverse the distance. You cannot send a photon through. You cannot send information through. You certainly cannot send a human being through. The bridge exists, but it is fundamentally, provably, non-traversable. This should have been the end of the story. Physics proved that the universe's tunnels are real, but useless. Case closed. But the word wormhole hadn't even been invented yet when Fuller and Wheeler published their proof. That honor belongs to John Archibald Wheeler himself, one of the most creative minds in 20th century physics. Wheeler was the kind of scientist who named things. He popularized the term black hole in 1967, and in 1957, in a paper with Charles Misner titled Classical Physics as Geometry, published in Annals of Physics, he coined the term that would capture the public imagination for generations. Wormhole. Wheeler's notebooks show the first recorded use on November 13, 1955. He named it after something beautifully simple: a worm eating through an apple. If you're an ant walking along the surface of an apple, the shortest path from one side to the other is the long way around the curved skin. But if a worm has burrowed straight through the middle, there's a shortcut that cuts right through the interior. Wheeler imagined the same thing happening in the fabric of space itself. And then Wheeler proposed something even stranger. He suggested that at incredibly tiny scales, space-time itself might not be smooth at all. At the Planck scale, about 10 to the negative 35 meters, which is so small that atoms look like galaxies by comparison, Wheeler theorized that quantum uncertainty would cause violent fluctuations in the curvature and topology of space. He called it quantum foam. In this picture, space-time at the smallest possible scale froths and churns like the surface of a boiling ocean, with microscopic wormholes constantly appearing, connecting random points in space, and then vanishing before anything can pass through them. If Wheeler was right, the fabric of reality is riddled with tiny wormholes at every moment, trillions upon trillions of them, flickering in and out of existence beneath the resolution of any possible measurement. The universe might be far more connected than it appears, and not connected in some vague, metaphysical way, connected through actual geometric tunnels in space-time, each one lasting for a fraction of a second, each one too small to see, too brief to use, but real in the same way that virtual particles popping in and out of the vacuum are real. Wheeler was a man who took ideas like this seriously. He had trained about 50 PhD students at Princeton, among them Kip Thorne and Richard Feynman's close collaborators. He co-authored the textbook Gravitation in 1973 with Misner and Thorne, a book so massive and so comprehensive that it is still the standard reference for general relativity over 50 years later. Wheeler thought big. He asked questions that made other physicists uncomfortable. Questions about the nature of existence itself, about whether the universe requires observers to be real, about whether physics and information are somehow the same thing. He spent his entire career arguing that the question is the answer, that the act of asking the right question contains within it the seeds of understanding. But even Wheeler couldn't make wormholes traversable. None of these wormholes, not the Einstein-Rosen bridge, not the quantum foam tunnels, not any solution anyone had found, allowed anything to pass through. The consensus was firm. Wormholes existed in the math, and the math said you could not use them. For over 2 decades after Fuller and Wheeler's 1962 proof, the subject of wormhole traversal was essentially dead. Physicists studied wormholes as mathematical objects, as tools for understanding the structure of spacetime, but nobody seriously investigated whether you could travel through one. Why bother? The proof was right there. Non-traversable. End of discussion. There were a few quiet developments during those years. In 1973, 2 physicists working independently on opposite sides of the Cold War divide, Homer Ellis in the United States and K.A. Bronnikov in the Soviet Union, found a new type of wormhole solution that was actually traversable. The Ellis-Bronnikov wormhole, as it came to be called, was held open by a phantom scalar field, a type of exotic matter with negative kinetic energy. It was the first traversable wormhole ever discovered, but it went largely unnoticed. The physics community wasn't ready for it. The paper received minimal attention and was essentially forgotten for over a decade. And then, in 1985, a science fiction writer picked up the phone and changed everything. Carl Sagan was writing Contact, the novel that would become one of the most beloved science fiction stories of the 20th century. He needed his protagonist, Eleanor Arroway, to travel from Earth to the star Vega, about 26 light years away. And he needed her to do it in a way that was scientifically plausible. His first draft had her fall into a black hole and pop out near Vega. It was dramatic, it was cinematic, and it was completely wrong. Falling into a black hole means crossing an event horizon from which nothing returns. It means being torn apart by tidal forces as gravity stretches you into a thin strand of atoms. It means a death, not transportation. Sagan knew he needed help, so he called his friend Kip Thorne. Thorne was the Richard P. Feynman Professor of Theoretical Physics at the California Institute of Technology, one of the most respected relativists on the planet. He would later win the Nobel Prize in Physics in 2017 for his contributions to the LIGO gravitational wave detector. But in 1985, he was a brilliant theorist who happened to be friends with a novelist in trouble. And as Thorne later recounted, of course he would help. Sagan was a friend. The book was fun, but Carl was indeed in trouble. The black hole method was a dead end. During a family trip, Thorne came up with an alternative. What if an infinitely advanced civilization had figured out how to stabilize a wormhole? What if they had discovered some exotic form of matter that could hold the throat open long enough for a spacecraft to pass through? It wouldn't violate any known law of physics exactly. It would require material that might not exist. But there was no theorem saying it was strictly impossible. Sagan loved it. He rewrote the novel with a wormhole at its center, attributing the exotic material to an earlier alien civilization so he wouldn't have to explain the physics in detail. Contact was published in 1985 to enormous acclaim and was later adapted into a 1997 film starring Jodie Foster. The Sagan-Thorne connection itself has a beautiful backstory. Film producer Linda Obst had set Sagan and Thorne up on a blind date sometime around 1979 or 1980. They became close friends, and that friendship would ripple through both science fiction and theoretical physics for decades. It was Obst who would later bring Thorne into the Interstellar project, connecting a chain from Sagan's phone call in 1985 to one of the most scientifically accurate films ever made in 2014. A blind date led to a friendship, which led to a phone call, which led to a paper, which led to a film, which led to a generation of people seeing what a wormhole actually looks like for the first time. Physics is unpredictable that way. But here is the part that matters more than the novel or the movie. Thorne didn't just help Sagan and move on. The problem captivated him. He went back to Caltech and assigned it to his graduate student, Michael Morris. And together, they did something that had never been done before. They sat down and rigorously asked, what would a traversable wormhole actually require? Their paper was published in 1988 in the American Journal of Physics. The title was Wormholes in Spacetime and Their Use for Interstellar Travel, and the subtitle gave away the game. A tool for teaching general relativity. Thorne framed it as a pedagogical exercise, but it was far more than that. Morris and Thorne constructed a completely new metric, a mathematical description of spacetime that described a wormhole you could actually travel through without dying. Their metric had two critical features. First, the redshift function had to remain finite everywhere. If it blew up to infinity at any point, you'd have an event horizon, and an event horizon means a one-way trip into oblivion. Second, the shape function had to satisfy specific geometric constraints to keep the throat open. And when Morris and Thorne worked through the math, they discovered the catch. The terrible, beautiful, physics-defining catch. A traversable wormhole requires exotic matter, not exotic in the casual sense, like some rare element from the periodic table. Exotic in the deeply unsettling sense. Matter with negative energy density. Material that has less energy than completely empty vacuum. If normal matter attracts gravitationally, exotic matter repels. If you push it, it accelerates toward you. If you pull it, it accelerates away. It violates something called the null energy condition, one of the foundational assumptions of classical physics that says the energy measured along any light ray is never negative. No known substance in the universe has this property. No experiment has ever produced macroscopic negative energy. No theory of particle physics predicts that it can be manufactured. Think about what negative energy actually means for a moment. Every object you have ever touched, every star you have ever seen, every particle that has ever existed in the observable universe has positive energy. Energy is what makes things move, what holds atoms together, what powers the sun, what gives mass to everything. Negative energy would be the opposite of all of that. It would be stuff that weighs less than nothing, that gravitationally repels instead of attracts, that makes space-time curve in the opposite direction from everything else in the universe. If you could hold a ball of negative energy in your hand, which you cannot, it would push your hand upward instead of resting in your palm, and you would need a staggering amount of it. Some physicists tried to find ways around this requirement. Matt Visser, a New Zealand-based physicist who earned his PhD at UC Berkeley and eventually became a professor at Victoria University of Wellington, developed what he called thin shell wormholes in 1989. His approach was elegant. Take two copies of a spacetime, Like two Schwarzschild black hole solutions, cut away the interior of each one, everything inside some radius beyond the event horizon, then glue the remaining pieces together at their boundaries. Using mathematical conditions developed by physicist Werner Israel in 1966, called the Darmois-Israel junction conditions, Visser showed that you could calculate exactly how much exotic matter was needed at the junction. The brilliant part was that this construction confined all the exotic matter to an infinitesimally thin shell right at the throat. Instead of needing exotic matter distributed throughout an entire region of space, you only needed it concentrated in a razor-thin layer. And Visser demonstrated that with the right matching, the total amount of exotic matter could theoretically be made arbitrarily small. Not zero, though. Never zero. You could minimize it, squeeze it down, make it as tiny as you wanted, but you could never eliminate it completely. Any traversable wormhole, no matter how cleverly constructed, demanded at least some exotic matter. Visser went on to write the definitive textbook on the subject, Lorentzian Wormholes, published by AIP Press in 1996, a 412-page monograph with 38 figures that systematically classified every known type of wormhole. He is one of the few physicists who has dedicated his career to mapping the complete landscape of wormhole possibilities, and his assessment captures the bittersweet reality of the field perfectly. But Morris and Thorne were very careful about how they phrased their conclusion. They did not say, traversable wormholes are impossible. They said traversable wormholes require material that we don't know how to make and might not exist. There is a critical difference. One is a proof of impossibility. The other is an acknowledgement of ignorance. And Thorne, ever the optimist, celebrated this distinction. He wrote that no type of thought experiment pushes the laws of physics harder than asking what an infinitely advanced civilization could do and what even they could not. A science fiction novelist had inspired one of the most rigorous theoretical physics papers of the 20th century, and that paper has been cited over 395 times, spawning decades of research into energy conditions, time machine physics, and the fundamental structure of spacetime. But the exotic matter problem was just the beginning of the bad news. Because even if you somehow got your hands on enough of this impossible material, the universe has stacked at least half a dozen additional obstacles between you and the other side of a wormhole. And each one, on its own, is probably enough to make traversal impossible. So let's walk through all of them. First, the amount of exotic matter you would need. In 1996, Larry Ford and Thomas Roman published a calculation in Physical Review D that put real numbers on the problem. For a wormhole with a throat radius of 500 meters, which is barely big enough to fit a spacecraft through, you would need approximately 3.367 times 10 to the 29th kilograms of negative mass. That is roughly 100,000 times the mass of the entire Earth, but with energy less than nothing. To put this in perspective, the total mass of the Earth is about 6 times 10 to the 24th kilograms. You would need to somehow create a ball of negative energy equivalent to 100,000 Earths and concentrate it into a region smaller than the length of a few city blocks. And it gets worse. For a related concept called the Alcubierre warp drive, which uses similar exotic matter to compress space in front of a ship and expand it behind. Physicists Thomas Fenning and Larry Ford calculated that traveling at 10 times the speed of light would require negative energy equivalent to roughly 10 billion times the mass of the entire visible universe. The numbers are not just large, they are absurd. They are the universe's way of saying absolutely not. But wait, there is one known source of negative energy in the universe. Just one. And when you hear about it, you'll understand why it doesn't help. In 1948, a Dutch physicist named Hendrik Casimir predicted something remarkable. If you take two perfectly conducting metal plates and bring them very close together, closer than a micrometer, something strange happens in the space between them. Empty space is not actually empty. It seethes with quantum vacuum fluctuations, virtual particles constantly popping into and out of existence in every wavelength imaginable. Outside the plates, all wavelengths of these fluctuations can exist freely, but between the plates, only fluctuations that fit neatly between them can survive. Long wavelengths are excluded, the way a long organ pipe can produce low notes, but a short pipe cannot. This restriction means the energy density between the plates is slightly lower than the energy density of the vacuum outside. In other words, the space between the plates has negative energy relative to normal vacuum. This is the Casimir effect, and it was experimentally confirmed by Stephen Lamoureux at Yale in 1997. The Casimir effect is real, measured, and reproducible. It is genuine negative energy. So why doesn't it solve the wormhole problem? Because the numbers are laughably small. At a plate separation of 100 nanometers, the Casimir force is only a few hundred piconewtons, and the negative energy density is about 10 to the negative third joules per cubic meter. A wormhole sustained entirely by Casimir energy would have a throat radius of roughly 10 to the negative 35 meters. That is the Planck length. It is 20 orders of magnitude smaller than a proton. You could fit approximately 10 to the 20th of these wormholes inside a single hydrogen atom. This is not a tunnel you can fly through. This is a tunnel that makes subatomic particles look like planets by comparison. But let's set aside the exotic matter problem entirely. Let's imagine, just for the sake of argument, that some civilization a billion years more advanced than us has figured out how to produce negative energy in bulk. They've built their wormhole. They've propped the throat open. Can they use it? Still probably not. Because of the instability problem. Without exotic matter actively holding it open, a wormhole's throat experiences gravitational attraction from any positive energy content passing through it. Matter, radiation, even your own body's mass energy would cause the throat to constrict. The Einstein field equations are unforgiving on this point. The geometry responds to energy, and positive energy makes the throat shrink. Imagine walking through a hallway where the walls close in a little bit with every step you take. Except the walls are made of space-time itself, and they close at the speed of light. You haven't even made it halfway through before the throat has pinched shut around you, trapping you inside a singularity. This isn't a slow, manageable squeeze. It's a catastrophic collapse that happens in a fraction of a second. Physicists have studied this instability extensively. Recent work from 2024 and 2025 on scalar perturbations, which are mathematical test fields sent through wormhole geometries, shows that the perturbations develop complex eigenfrequencies with unstable modes that grow exponentially over time. In plain language, even the smallest disturbance to a wormhole grows rapidly out of control, like a tiny crack in a dam that widens until the whole structure fails. The wormhole doesn't just collapse, it violently self-destructs. And even if you somehow solve that problem, there's quantum back reaction. Stephen Hawking showed in 1992 that if a wormhole is configured in a way that would allow time travel, vacuum fluctuations experience exponential blue shifting as they circulate through the loop. The energy density builds in a runaway feedback cycle, growing without bound until the accumulated energy destroys the wormhole from within. The very attempt to use a wormhole as a time machine triggers its own destruction. This led Hawking to one of the most famous conjectures in modern physics. He called it the chronology protection conjecture, published in Physical Review D in 1992. Hawking proposed that the laws of physics do not allow the appearance of closed time-like curves, which are paths through space-time that loop back to their own starting point, enabling travel into the past. He argued that quantum effects would always intervene to prevent the formation of time machines, no matter how clever the engineering. Hawking even gave his enforcement mechanism a name. He called it the Chronology Protection Agency, a tongue-in-cheek reference to science fiction police forces, whose job, he said, was keeping the world safe for historians. And he offered what might be the most elegant empirical argument against time travel ever articulated. The best evidence we have that time travel is not possible, he said, and never will be, is that we have not been invaded by hordes of tourists from the future. It is hard to argue with that logic, and the theoretical obstacles keep piling up. In 1993, John Friedman, Kristin Schleich, and Donald Witt at the University of British Columbia proved the topological censorship theorem. Published in Physical Review Letters, it states that in any spacetime satisfying the null energy condition, every causal curve connecting the distant past to the distant future is equivalent to a topologically trivial path. In plain language, if energy behaves normally, then every path through spacetime is equivalent to one that doesn't pass through any tunnels or handles or wormholes. The shortcut is forbidden. The topology of physically reasonable isolated systems is shrouded from distant observers. You can't see it, and you can't use it. Then there are the energy conditions themselves, which form the mathematical backbone of why wormhole traversal fails. Physicists define four main ones, and they function like the load-bearing walls of a building. You can redecorate the interior all you want, but if you knock out the load-bearing walls, the whole structure collapses. The null energy condition says the energy density along any light ray is non-negative. The weak energy condition says every observer measures non-negative energy. The strong energy condition says gravity is always attractive. And the dominant energy condition says energy cannot flow faster than light. These sound technical, but they have a simple collective meaning. Energy behaves in reasonable, predictable ways. It doesn't go negative. It doesn't outrun light. Gravity pulls. The universe follows the rules. A traversable wormhole requires violating at minimum the null energy condition, and probably the weak energy condition too. That is like knocking out the most fundamental structural wall in the building of physics. These violations tend to create classical instabilities, quantum instabilities, or both. They open the door to perpetual motion machines, to infinite energy extraction, to all sorts of pathological behavior that has never been observed in nature. They are not just technical requirements. They are the universe's load-bearing walls, and removing them tends to bring the whole structure crashing down. And finally, even if every single one of these problems were solved, there are the tidal forces. Tidal forces are what happen when gravity pulls harder on one part of an object than another. The moon creates tides on Earth because it pulls harder on the near side of the ocean than the far side. Scale that up enormously, and you get what physicists call spaghettification, the stretching of an object into a long, thin strand as it approaches a compact gravitational source. For a wormhole with a 500-meter throat radius, which already requires those impossible 100,000 Earth masses of negative energy, the tidal force on a 1-meter object at the throat would be approximately 3.6 times 10 to the 11th newtons. To give you a sense of that number, the strongest materials ever engineered by humans can withstand forces of maybe a few billion newtons before breaking. The tidal force at the wormhole throat exceeds that by a factor of 100. Any spacecraft, any material, and certainly any human body would be stretched into atomic spaghetti long before reaching the other side. Morris and Thorne themselves acknowledged this. They imposed human comfort constraints on their traversable wormhole, requiring tidal accelerations no greater than 1 g and transit times less than 1 year, and found that these constraints made the exotic matter requirements even more extreme than the already impossible baseline. So here is where we stand. Wormholes are valid solutions to Einstein's field equations. They are mathematically real, but traversing one requires exotic matter that probably cannot exist in quantities that dwarf the mass of planets. The throat is unstable and wants to collapse. Quantum effects conspire to destroy any configuration that would allow time travel. Topological censorship forbids shortcuts in well-behaved spacetimes. The energy condition violations needed create fundamental instabilities, and the tidal forces at the throat would shred anything that tried to pass through. The universe seems to have built a door and then locked it with every lock it has. Story over, right? Not even close. Because starting in 2013, physicists discovered something that suggests wormholes are not just a curiosity or a dead end. They might be the key to understanding what space and time actually are. And this twist in the story came from two of the most brilliant minds in theoretical physics, connecting two ideas that Einstein himself had published in the exact same year. Here is one of the most extraordinary coincidences in the history of science. Remember, 1935? Einstein and Rosen published their bridge paper in July. But a few months earlier, in May, Einstein had published another famous paper with Boris Podolsky and the very same Nathan Rosen. The EPR paper, as it became known, described quantum entanglement, the phenomenon where two particles become correlated in such a way that measuring one instantly determines the state of the other, regardless of the distance between them. Einstein called it spooky action at a distance and thought it proved quantum mechanics was incomplete. He considered entanglement so absurd that he used it as an argument against quantum theory. So in the span of 2 months in 1935, Einstein published 2 papers, both with Rosen. One described a bridge connecting 2 regions of spacetime. The other described a mysterious link connecting two distant particles. Both papers carried the initials ER, and for nearly 80 years, nobody noticed that they might be describing the same thing. For nearly 80 years, nobody connected these two papers. The Einstein-Rosen bridge was a topic in general relativity. EPR entanglement was a topic in quantum mechanics. They lived in different textbooks, different departments, different intellectual universes. They were studied by different communities of physicists who rarely talked to each other. Then, in June of 2013, Juan Maldacena and Leonard Susskind published a paper that shook theoretical physics to its foundations. Maldacena is an Argentine-American physicist at the Institute for Advanced Study in Princeton, the same institution where Einstein himself worked. Born in Buenos Aires in 1968, educated at the Instituto Balcero in Argentina, and then at Princeton, where he earned his PhD in 1996 under Curtis Callan. Maldacena has been called perhaps the greatest theoretical physicist of his generation by Susskind. And that is not hyperbole. In 1997, at the age of 29, Maldacena published a paper that fundamentally changed how physicists understand the universe. The ADS/CFT correspondence showed that gravity in a particular type of curved spacetime called anti-de Sitter space is mathematically identical to a quantum field theory living on its boundary. Imagine that everything happening inside a room, all the gravity, all the matter, all the three-dimensional physics, could be perfectly described by a theory that lives only on the walls of the room. That is the essence of Maldacena's insight. It has been cited more than 15,000 times, making it the most cited paper in the history of high-energy physics. It won him the Breakthrough Prize in Fundamental Physics, the Dirac Medal, and the Albert Einstein Medal, among others. Susskind, the Felix Bloch Professor at Stanford, is one of the co-founders of string theory, having independently developed the idea around 1970, along with Yoichiro Nambu and Holger Nielsen. He formulated the string theoretic interpretation of the holographic principle in 1995, and he spent decades locked in a famous intellectual battle with Stephen Hawking over whether information is destroyed inside black holes, a debate chronicled in his popular book The Black Hole War, published in 2008. Susskind and Hawking disagreed so fundamentally that their debate defined an entire era of theoretical physics, spanning decades of conferences, journal articles, and occasionally sharp public disagreements. By 2013, Susskind had mostly won the argument, but the details of how information survives remained mysterious. Together, these two titans of theoretical physics proposed something breathtaking, something so simple and so radical that it took the entire physics community by surprise. They argued that Einstein-Rosen bridges and Einstein-Podolsky-Rosen correlations are the same thing, not analogous, not metaphorically similar, not vaguely connected, literally the same physical phenomenon viewed from two different perspectives. They called it R equals EPER. The paper, titled Cool Horizons for Entangled Black Holes, appeared in Fortschritte der Physik and laid out the argument with startling clarity. When two black holes are quantum mechanically entangled, they argued, they are connected through the interior by a wormhole. The entanglement is the wormhole. The wormhole is the entanglement. These are two descriptions of a single underlying reality. And they didn't stop at black holes. Maldacena and Susskind suggested that even the simplest entangled pair of particles might be connected by a wormhole. A very quantum, very tiny wormhole, far too small to send anything through, but a genuine geometric connection through space-time nonetheless. If this is right, the implications are staggering. It means that the universe is doing something beneath the surface that nobody suspected. Every time two particles become entangled in a laboratory, a microscopic wormhole connects them. Every quantum computer manipulating entangled qubits is, in some deep mathematical sense, creating and manipulating tiny tunnels through space. Every measurement of one entangled particle that instantly correlates with its distant partner is a signal traveling through a wormhole, too small to see and too brief to exploit, but geometrically real. The universe is not just sprinkled with wormholes, it is held together by them. The emptiness between stars, the space between atoms, the apparent void between entangled particles on opposite sides of a laboratory, all of it may be connected by a web of microscopic wormholes so dense and so fundamental that without them, space itself would not exist. This idea received powerful support from work by Mark van Ramsdonk, a physicist at the University of British Columbia, who in 2010 published a thought experiment that became one of the most discussed ideas in theoretical physics. Using the ADS/CFT correspondence, van Ramsdonk showed that if you take two quantum systems that are entangled and gradually reduce their entanglement, the corresponding space-time geometry stretches and thins the wormhole connecting them, reduce entanglement further, and the wormhole pinches off entirely. Remove all entanglement, and space-time itself disconnects into separate, unrelated fragments. The conclusion was extraordinary. Entanglement doesn't just correlate distant objects. It literally constructs space. Without quantum entanglement, there would be no connected space-time. Space would atomize into disconnected shards with no geometric relationship to each other. It would be like taking a sweater and cutting every thread. The shape doesn't just loosen. It ceases to exist as a coherent object. The threads are the sweater. An entanglement is the thread of space-time. The fabric of the universe is woven from quantum connections, and wormholes are the threads. This might sound like abstract philosophy, but it connects to one of the most concrete and bitterly contested problems in physics, the black hole information paradox. And this is a problem that kept physicists up at night for decades. In the 1970s, Stephen Hawking made a calculation that should have been routine, but turned out to be devastating. He showed that black holes are not completely black. They emit radiation, now called Hawking radiation, through a quantum mechanical process near the event horizon. Pairs of virtual particles constantly pop into existence everywhere in space, usually annihilating each other immediately. But near a black hole's event horizon, one particle can fall in while the other escapes. Over immense timescales, this process drains the black hole's energy. The black hole shrinks, and eventually it evaporates entirely. The problem is that this radiation appeared to be perfectly thermal, meaning random and featureless, carrying no information about what originally fell into the black hole. So if you threw a copy of Shakespeare's complete works into a black hole and waited for it to evaporate, the radiation that came out would tell you nothing about Shakespeare. The information would be gone, destroyed. And that violates a fundamental principle of quantum mechanics called unitarity, which says that information can be scrambled, reshuffled, and hidden, but never truly destroyed. If Hawking was right, quantum mechanics was broken at the deepest level. The debate lasted over 40 years. Hawking himself initially believed information was lost. Susskind and others were convinced it wasn't. At one point, Hawking famously bet Kip Thorne and John Preskill, an encyclopedia, that information was destroyed. He later conceded the bet to Preskill, but not to Thorne, in a concession that Preskill described as somewhat unsatisfying because Hawking's reasoning for conceding was not entirely clear. And then, in 2019 and 2020, a series of breakthroughs involving wormholes pointed toward a resolution that stunned the community. Physicists, including Jeff Pennington at Stanford, Ahmed Al-Maheri, Juan Maldacena, and others, developed what became known as the island formula. They showed that when you include wormhole geometries in the gravitational path integral, which is a mathematical technique for summing over all possible spacetime configurations, you get the correct answer for how much information a black hole has radiated at any given time. The result follows what's called the Page curve, named after physicist Don Page, which predicts that information starts leaking out of a black hole approximately halfway through its evaporation. Before the Page time, the radiation looks random. After it, information begins to emerge, and the mathematical structures that make this work are wormholes connecting the radiation to the black hole interior. The key insight was that distant regions of spacetime that appear disconnected are actually linked through wormhole-like geometries called replica wormholes. As physicist Raghu Mahajan explained it, things you thought were independent are not really independent. The wormholes create hidden connections that allow information to escape without traveling faster than light. The information isn't destroyed. It's encoded non-locally and gradually re-emerges in the Hawking radiation through channels that look, in the mathematics, exactly like wormholes. This was a major result, published in Reviews of Modern Physics in 2021, and it suggested that wormholes are not just theoretical curiosities. They may be essential to understanding how quantum information works in a gravitational universe. But then something happened that took the wormhole story from the pages of theoretical physics journals to the front page of every news outlet on the planet. And it started a controversy that is still reverberating through the physics community. On November 30th, 2022, the journal Nature published a paper with a headline-grabbing claim. A team of physicists said they had created a traversable wormhole using Google's Sycamore quantum processor. The story exploded across every major news outlet. The New York Times covered it. CNN covered it. Social media lost its collective mind. For a brief, dizzying moment, it seemed like the line between theoretical physics and science fiction had been erased. Humanity had built a wormhole on a computer chip in a lab in California. The lead authors were Daniel Jafferis of Harvard, Alexander Zlokapa of MIT, and Maria Spiropoulou of Caltech, with Hartmut Neven of Google Quantum AI. The paper was titled Traversable Wormhole Dynamics on a Quantum Processor, and the media coverage treated it as though physicists had punched a hole in space. the reality was more complicated and, honestly, more interesting than the headlines suggested. What the team actually did was build a 9-qubit quantum circuit that simulated a simplified version of something called the Sachdev-Ye-Kitaev model, or SYK model. This is a quantum mechanical system that has a known mathematical dual, a corresponding description in the language of gravity that involves two-dimensional anti-d sitter spacetime. In that gravitational dual description, transmitting quantum information through the circuit corresponds to a particle traversing a wormhole. The researchers used machine learning to reduce the SYK Hamiltonian from 210 terms to just 5, preserving key properties that they argued were gravitationally relevant. They then demonstrated quantum teleportation through this simplified circuit and interpreted the results as consistent with wormhole traversability in the dual description. But no physical wormhole was created. No tunnel opened in the laboratory. No particle traveled through a shortcut in space. What they had done was simulate quantum dynamics on a quantum computer and then interpreted those dynamics through the lens of a mathematical duality. The wormhole existed only in the abstract, holographic interpretation, not in our three-dimensional universe. Computer scientist Scott Aronson of the University of Texas at Austin put it bluntly. If this experiment has brought a wormhole into actual physical existence, he said, then a strong case could be made that you, too, bring a wormhole into actual physical existence every time you sketch one with pen and paper. And then the scientific challenges arrived. In February 2023, Norman Yao of Harvard, along with Bryce Coburn and Thomas Schuster, published a critical analysis with findings that cut deep. They showed that the 5-term Hamiltonian the team used was what's called fully commuting, meaning the mathematical operators all work independently without interfering with each other. This is a problem because chaotic scrambling, where information becomes rapidly mixed and delocalized, is a defining property of black holes and a necessary condition for the gravitational interpretation to hold. Without scrambling, you don't have a system that behaves like gravity. You just have a simple quantum circuit, even more damaging. The critics showed that the specific signature the team pointed to as evidence of gravitational behavior, something called perfect size winding, appears in many simple non-gravitational systems purely by coincidence. And when they scaled the simulation to larger systems, the signature disappeared entirely, suggesting it was an artifact of the tiny system size rather than a genuine gravitational signal. Quantum magazine, which had initially run a headline suggesting physicists had created a wormhole using a quantum computer, changed its headline to include the word holographic and later published an extensive article titled Wormhole Experiment, called Into Question. Physicist John Preskill of Caltech, one of the most respected voices in quantum information, stated that the evidence for a gravitational interpretation was weakening. Now, to be fair to Jafferis and his collaborators, the underlying theoretical work that inspired the experiment is solid and significant. In 2016 and 2017, Jafferis, along with Ping Gao and Aaron Wall, published a groundbreaking paper showing that adding a specific interaction between the two boundaries of an eternal black hole creates a quantum matter stress tensor with negative average null energy. making the Einstein-Rosen bridge traversable. This was the first traversable wormhole solution embedded in a complete quantum gravity framework, and it demonstrated something profound. Traversable wormholes in gravity are mathematically equivalent to quantum teleportation. They are the same process, described in two different languages. The Google experiment was attempting to verify this theoretical insight in the laboratory. The theory is almost certainly correct. The question is whether this particular experiment actually demonstrated it, and the answer, according to many physicists, is probably not. This entire episode is actually a case study in how science communication can go wrong. The theoretical physics was real. The mathematical relationship between traversable wormholes and quantum teleportation is one of the most profound discoveries of the last decade. But the gap between what the experiment showed and how it was communicated to the public was enormous. Saying you created a wormhole on a quantum computer when what you actually did was simulate 9 qubits in a simplified model whose gravitational interpretation is disputed is the kind of overstatement that erodes public trust in science. And in a field where the actual results are fascinating enough, the hype was unnecessary. But this episode reveals something important about the current state of wormhole physics. The field has moved far beyond the question of whether humans will ever fly through a wormhole. That answer is almost certainly no. The interesting questions now are about what wormholes teach us about reality itself. And those lessons are turning out to be far more valuable than any shortcut through space. Consider what we have learned. If ER equals EPR is correct, then every entangled pair of particles in the universe is connected by a microscopic wormhole. The fabric of spacetime is not a pre-existing stage on which physics happens. It is constructed, woven together by quantum entanglement, with wormholes as the geometric expression of those connections. Remove the entanglement, and space falls apart. Spacetime is emergent, not fundamental. It arises from something deeper, something quantum mechanical, something we are only beginning to understand. This is arguably the most profound shift in our understanding of space, since Einstein himself showed that space and time are not absolute but dynamic, curved by matter and energy. If the early 20th century taught us that space-time is flexible, the early 21st century may be teaching us that space-time is built, and wormholes are teaching us something else too. They may be the key to resolving the deepest incompatibility in all of physics. General relativity and quantum mechanics are both spectacularly successful theories. General relativity describes gravity, the large-scale structure of the universe, the bending of light, the expansion of space. It works beautifully for planets, stars, and galaxies. Quantum mechanics describes atoms, particles, forces, everything on small scales. It powers every computer chip, every laser, every MRI machine. Both theories have been tested to extraordinary precision, and neither has ever failed a single experimental test. But the two theories are mathematically incompatible. They use different languages, different assumptions, different mathematical structures. General relativity treats spacetime as smooth and continuous. Quantum mechanics demands discreteness and uncertainty. When you try to apply quantum mechanics to gravity, you get infinities that cannot be tamed by any known technique. When you try to apply general relativity to quantum particles, you get paradoxes that cannot be resolved within either framework. Unifying them into a single theory of quantum gravity is the greatest unsolved problem in physics, and it has remained unsolved for nearly a century, despite the efforts of thousands of brilliant physicists. Wormholes sit exactly at the intersection. They are structures described by general relativity that exhibit quantum properties. Studying them forces physicists to confront the places where the two theories conflict and to develop new mathematical tools that might eventually bridge the gap. Matt Visser, the New Zealand-based physicist who wrote the definitive textbook on wormholes, Lorentzian Wormholes, published in 1996, has argued that whatever the true theory of quantum gravity turns out to be, it must reproduce wormhole physics in the appropriate limit. Wormholes are not just a curiosity. They are a test case for any theory that claims to describe the quantum nature of gravity, and Visser himself has captured the bittersweet state of the field with characteristic honesty. The good news, he has said, is that after about 10 years of hard work, we cannot prove that wormholes don't exist. The bad news is that they need large amounts of negative mass to hold them open. There is something almost poetic about the way pop culture has handled wormholes. Almost every depiction gets them wrong, but the one that got them most right was made by the very physicist who defined the field. When Christopher Nolan was developing Interstellar, he brought on Kip Thorne not just as a consultant, but as an executive producer. Thorne established two ground rules. Nothing in the film would violate established physical laws, and all speculation would spring from science, not from screenwriter imagination. Nolan agreed with one condition. The science couldn't get in the way of making a good movie. Thorne spent 2 weeks convincing Nolan that faster-than-light travel was impossible. 2 weeks. Nolan eventually accepted. For the wormhole and the black hole gargantua, Thorne worked out the exact equations for tracing light rays through curved spacetime, and the visual effects team at Double Negative in London rendered them faithfully. This was not a case of a scientist waving his hands and saying, "Make it look spacey." Thorne provided actual equations, and the team wrote new rendering software to solve them. The computation required about 800 terabytes of data for some of the black hole scenes. Individual frames took up to 100 hours to render. The resulting images were so scientifically interesting that they were published in a peer-reviewed paper in 2015 titled Visualizing Interstellar's Wormhole, authored by visual effects supervisor Oliver James, lead artist Eugenie von Tunzelmann, producer Paul Franklin, and Thorne himself. It was the first time a Hollywood special effects team had co-authored a physics paper, and the film corrected one of the most persistent misconceptions about wormholes. Almost every prior depiction, Star Trek's Bajoran wormhole, Stargate's ring devices, countless others, showed wormholes as flat, two-dimensional portals, glowing doorways you step through. But a wormhole mouth in three-dimensional space would actually appear as a sphere. You would see the other side of the universe distorted and compressed into a floating, transparent globe hanging in space. Light from the destination would wrap around the spherical throat and reach your eyes from all directions, creating an image that is simultaneously disorienting and beautiful. When the crew of the Endurance approaches the wormhole in the film, they see Saturn's rings distorted through its spherical surface. Interstellar showed this correctly, and for millions of viewers, it was the first time they had ever seen what a wormhole would actually look like according to the equations of general relativity. But even Interstellar got one thing wrong, or at least glossed over one critical point. The film implies that an advanced civilization placed the wormhole near Saturn for humanity to use. It does not dwell on the fact that maintaining such a wormhole would require negative energy equivalent to the mass of multiple planets, that the throat would be violently unstable, that tidal forces would make passage dangerous or impossible, and that the very concept might be forbidden by topological censorship if the null energy condition holds. Maldacena himself has addressed the time travel implications of wormholes, noting that both quantum and gravitational constraints prevent wormholes from being used to travel faster than the speed of light in any meaningful sense. Due to extreme time dilation inside the wormhole, the journey would actually take longer from an outside observer's perspective than simply traveling through normal space. Even if wormholes existed, they would not help you get somewhere faster. They might connect distant regions of space, but they wouldn't save you any time. One physics communicator summed it up with a line that deserves to be in every documentary about wormholes. Even if they exist, they're not going to help Captain Sisko get to the Gamma Quadrant before dinner. So where does this leave us? What is the final verdict on wormholes? Here is what we know for certain. Wormholes are valid, rigorous solutions to Einstein's field equations. They are as mathematically real as black holes were before we observed them. They come in several varieties, from the original non-traversable Einstein-Rosen bridges to the traversable Morris-Thorne wormholes to the quantum scale froth of Wheeler's quantum foam. They require exotic matter with negative energy density to remain open, and no known physical process can produce this material in the quantities required. The only known source of negative energy, the Casimir effect, produces amounts so tiny that a Casimir-sustained wormhole would be smaller than a proton by a factor of 10 to the 20th. The throats are unstable. The tidal forces are lethal. The chronology protection conjecture suggests the universe actively prevents configurations that would allow time travel, and the topological censorship theorem forbids shortcuts in spacetimes where energy behaves normally. But here is what we also know. The ER equals EPR conjecture, proposed by two of the most respected theoretical physicists alive, suggests that wormholes are not just permitted by physics, but are fundamental to it. Every entangled particle may be connected by a microscopic wormhole. Space-time itself may be constructed from these connections. The resolution to the black hole information paradox appears to involve wormhole-like geometries that connect apparently disconnected regions of space, and the study of wormholes continues to produce insights into quantum gravity, the nature of information, and the deepest architecture of reality. Wormholes are real. They exist in the mathematics of our most successful theory of gravity. They may exist as the geometric shadow of quantum entanglement, the invisible threads holding the fabric of space together. They are teaching us things about the universe that we could not learn any other way, but as highways through the cosmos, as shortcuts for future astronauts, as portals to distant galaxies. Almost certainly not. the universe has made its position clear. It will show you the door. It will prove the door exists. It will even let you calculate exactly what the door looks like, how big it is, and where it leads, but it will not let you walk through it. Think about what we've covered. To hold a wormhole open long enough to send a single person through, you would need 100,000 times the mass of the Earth in a form of matter that has never been observed and probably cannot exist. The only known source of negative energy produces amounts so small that the resulting wormhole would be a billion times smaller than an atom. Even if you solved the energy problem, the throat would collapse on you faster than light. Even if you stabilized the throat, tidal forces would tear your body apart. Even if you survived the tidal forces, quantum effects would build to infinite intensity and destroy the wormhole from within. And even if none of that happened, the topological censorship theorem says the laws of physics simply do not permit the shortcut. The universe is not being subtle about this. And yet, in a strange way, that might be the most interesting thing about wormholes. Not what they could do for us as transportation, but what they are already doing for us as tools of understanding. Einstein didn't set out to build a shortcut through space in 1935. He was trying to remove singularities from his equations. Carl Sagan didn't set out to launch a new branch of physics in 1985. He was trying to get his character to Vega. Maldacena and Susskind didn't set out to explain the origin of spacetime in 2013. They were trying to reconcile two descriptions of black holes. In every case, the wormhole was not the destination. It was the lens that revealed something deeper. There is a beautiful irony in the fact that Einstein published both the bridge paper and the entanglement paper in the same year, both with the same co-author, and never suspected they were related. He spent the last 30 years of his life searching for a unified theory that would connect gravity and quantum mechanics, and the connection was right there in his own work. Two papers sitting side by side on his desk, each containing half of an insight that wouldn't be completed for another 78 years. If there is a lesson in that, it might be that the universe has a sense of humor about revealing its secrets. It shows you the pieces and waits to see how long it takes you to put them together. We're still putting them together. The ER equals EPR conjecture is not proven. The island formula is a breakthrough, but the full theory of quantum gravity remains elusive. Wheeler's quantum foam has never been directly observed. We don't know whether space-time really is emergent, whether entanglement really does build space, whether the wormhole-like structures in the gravitational path integral are real geometric objects or mathematical tricks. But here is what is certain. Every time physicists have studied wormholes, they have learned something unexpected about the universe. Every time they have tried to prove wormholes impossible, they have instead found that the impossibility reveals a deeper truth. And every time the story seemed over, a new chapter opened. John Wheeler spent his career arguing that the question is the answer, that the right question, asked the right way, contains within it the seeds of understanding. Wormholes may be the ultimate example of this principle. They are a question that physics keeps asking and the universe keeps answering in increasingly surprising ways. Not with a tunnel you can fly through, but with a window into how reality is built. The math says wormholes are real. The physics says you cannot travel through them. And the science says that might be exactly the point. If you want to see what happens when physics gets even stranger than wormholes, check out the video on screen now. And if you made it this far, subscribe. There is a lot more universe to cover.